All right. So now we're going to switch gears for a bit and talk about fatigue. So, whereas fracture toughness, we're looking at resistance to brittle fracture, which is a very rapid process, fatigue is looking more at lifetime and slow progressive failure. And so, when we talk about fatigue, what we mean is we have failure during lengthy cycles of repeated stress. So it's a whole different kind of failure that's exhibited. And so the stress varies with time, and some of our key parameters that we're going to look at are S, sigma m, and the frequency. So how often. And so when we're looking at fatigue, it's important because obviously fatigue can cause failure, but it does so at applied stresses that are much lower than our design criteria, such as yield strength. And um, so it's stuff that we're not designing for based on yield or static plastic deformation, but because it's over time and cyclic, it can happen at much lower stresses. And in fact, it's responsible for a majority of mechanical engineering failures, so 90% roughly. All right. So how do we test this, and what does it look like, and what is it trying to mimic? So this is kind of a device that's meant to fatigue test a material. And so we have our specimen here. You can see it kind of looks similar to a dog bone. And we have it housed in this apparatus. And basically, it's being rotated by this motor that's controlling the frequency, and we're applying a load to that rotation. And so it's going to be basically cycling through that that load that's applied, and therefore that gives us that frequency and so forth. So that's kind of what we're looking at with this. And the most common kind of data that we look at is known as SN. So this is what fatigue data typically comes in. So S is short for stress, in this case, stress amplitude, and then N signifies the number of cycles. So basically, what applied stress are we putting, and how many cycles to, is it being tested for? So fatigue strength is the stress amplitude at which failure will occur in a given number of cycles, right? So if I pick a stress to apply, how many cycles is it going to take to fail that sample? And so you see that basically the higher the stress amplitude is, the smaller the number of cycles it can take to fracture. Whereas if you lower the stress, it can handle more cycles. And so that's kind of what the general curve is showing you. So at S1, so amplitude, stress amplitude S1, if we follow this curve, we see that it can handle, this is the fatigue life at that. And so you can get a number here, and this is in terms of a log scale of the number. So fatigue life is then said to be the number of cycles to cause failure at a specific stress. So we're looking at kind of the relationship between the stress that is under for the test and the cycles it can withstand. Another important thing that often comes up for specific types of materials is a fatigue limit. And so that's basically a limiting stress amplitude S below which failure doesn't occur. And so that's obviously a very important thing. That's great because otherwise it would continually decrease and decrease, right? So this is only for some materials. So it's certain ferrous and titanium alloys can kind of exhibit this fatigue, or sometimes referred to as an endurance limit. And so if we look at that same SN curve, we see that this is what we're kind of talking about. So initially, if the stress is high, you see it can withstand a small number of cycles, and then the number of cycles increases as we decrease the stress to a point, right, where if you lower it below this fatigue limit, it continues, it won't fail, right? Essentially, it can keep going if it's below this fatigue limit. So basically, that's important because that will not cause failure. Basically, with infinite cycles, and so obviously that's a great scenario to be in. All right, so we can look at some actual materials that exhibit this fatigue limit. And again, I said we mentioned some iron and titanium alloys, and you see here that here's the titanium alloy up here with aluminum and tin, and you see it kind of levels off. We also have 4340, which has the same kind of feature here. There's 1045 steel, cast iron. You can see has that. And so you can kind of just see that that levels off, and those are obviously good conditions to be under. Whereas this one right here, for comparison, doesn't really exhibit. It just keeps going down, right? All right. So if we're looking at a sample that has failed under these cyclic loading conditions, there's some giveaways to indicate that it is fatigue. And that would be these kind of striations that we see. So you can see a very striated surface. This is under TEM. This is under sort of optical strain. And so basically there's kind of two different progressions. You can have kind of a slow crack progression. And again, it's cyclic, so it's not happening rapidly for the most part in this region. However, it gets to the point where it can no longer handle that. And so then you have a more rapid failure. So this is kind of indicative of that fatigue striation area where there's more slow crack generation. So essentially, you can think of kind of each one of these being related to a specific cycle in that condition, right? So that's kind of a giveaway for fatigue or an indicator of fatigue failure in materials.